of functions. Sorry, not parity, we did it last time, about periodicity of the following functions. First of all, let us circle the definition of a periodic function. So we have definition, real function g with domain dg is said to be periodic or period P, which is with period P, periodic of period P, if there exists real P greater than 0, such that for all x in dg we have x plus p. Sometimes we write plus minus p, and sometimes we write x plus k pk in z. Must belong to dg, so we have x for all x in dg, x plus p is in dg, and g of x plus p is equal to g of x for all x in dg, and x plus p for in dg. If these two conditions are verified, then we said that p is a period. The smallest one, the least one on all the period p is called sometimes primitive, the smallest p, and sometimes you can find it as a period. The smallest one is called a period, or the period of the function. All things considered, let us start by f1. But here, the fact that for all x in dg there exists there exists p real, such that for all x in dg, x plus p is in dg, and this equation is verified, is true for all x in dg. This is very important, because when we suspect that the function is not periodic, we show that for a given x we have not this equation, it is not verified, so we have no p, no period, such that this is true. I will explain this with examples. Let us start by this, which is a little bit difficult. Does f1 is periodic, and if it is periodic, what is its period? I suspect that f1 is not, I suspect that f1 isn't periodic. Then I will try to verify that this is true. If f1 is periodic, this means that there exists p greater than 0. Its domain of definition is, the domain of definition of f1 is R. So we have no problem with adding p to x even any given x. Does there exist a period such that f1 of x plus p is equal to f1 of x for all x in dg df1, which is equal to R? If this is true, this makes f1 periodic. If we cannot find p such that this is true, so f1 will be non-periodic. If we take x equal to 0, suppose that this is true. So if we take x equal to 0, then we will be able to find p greater than 0, such that what? Such that f1 of 0 plus p equal to f1 of 0. This means that f1 of 0 is equal to 0, and f1 of 0 plus p is equal just 3p minus p power 3 plus 3p power 7. This is equal to 0, which is equivalent to p times, we take p as a factor, common factor, p times 3p power 6 minus p power 2 plus 3 equal to 0. Then p is equal to 0, which is rejected, since the period must be strictly greater than 0. So this is rejected. We should solve the equation 3p power 6 minus p power 2 plus 3 equal to 0. Let us set p square equal to chi. Then we put f of chi equal to 3 chi square minus chi plus 3, power 3 minus chi plus 3. Since we put chi equal to p square, this means chi is positive. So we study this function from 0 to plus infinity, and we study this function from 0 to plus infinity. F prime with respect to chi, this is equal to 9 chi squared minus 1, which is equal to 3 chi minus 1 times 3 chi plus 1. This is the derivative. We stand the table of variation. Table of variation start from 0 to plus infinity. Here we have chi, here we have f prime, and here we have f. The solutions are chi equal to 1 over 3 and minus 1 over 3, but we'll reject this one since we set chi equal to p square. Here is equal to 0, and in this interval it is negative, and in this interval it is positive. F of 0 is equal to 3, and it is increasing until f of 1 divided by 3, then it goes to plus infinity. So the minimum value is f of 1 over 3, and f of 1 over 3, this function, is equal to 1 over 9 minus 1 over 3, so minus 2, I think minus 2 over 9 plus 3, this, which is strictly greater than 0. This means what? This means that this equation has no solutions. This means that there is no p such that this is true. So the equation, the previous equation, f of f1 of 0 plus p equal to f1 of 0. Since this is not true, to be periodic, we need to verify that there exists p such that for all x in the domain of definition, we have f1 of x plus p equal to f1 of x. Since for 0 it is not true, we cannot find any p such that the equation is verified. This means that f1 isn't periodic at all. This is a different manner to answer this question. And here we are about the first question. How about the second function, f2? f2 x, this is equal to the fifth root of 1 minus x squared plus the fifth root of 1 plus x squared. Once again, I suspect that this function isn't periodic. What we can do, we can, for example, take x equal to 1. If f2 is periodic, this means that the domain of definition of this function is R. So the f2 is equal to R. If this function is periodic, this means that there exists p greater than 0, such that what? Such that for all x in R, p plus x plus p is sure in R, and f2 of x plus p for all x in R in the domain of definition. Here we choose a quiet number which fits our to a simple calculation. So we will take x equal to 1 to get here 0. What we will get? We will get f2 of 1. This should be equal to f2 of 1 plus p. Does such p exist? If this p exists such that this is verified, this means that this is verified. If we cannot find p such that this is true, this means that we have no legislation for all x in R. This means that there is no period. And this equation is transformed to f2 of 1. This means that the square root of 2 squared, the fifth, we have 1 plus 1 squared for the fifth, and here we have 0. This is equal to what? This is equal to the square root, the fifth root of 1 minus p minus x, 1 minus 1, this 1 plus p, this means 1 minus 1 minus p, 1 minus 1, 0, minus p squared. This means that p squared plus the fifth root of what? Of 1 plus 1 plus p. This means 2 plus p squared. Yeah. We have this equation. Let us divide by p, by this term, both equation. We will get what? We will get p is supposed to be strictly greater than 0. This means that we will get the fifth root of 2 divided by p squared equal to 1 plus the square root of here 1 plus p divided by, we divided, sorry, here we get 2 divided by p, we have square, plus 1 square. And actually this equation has no solution. It has no solution. There is no p such that this is true. Why? Because we have here the fifth root of 2 divided by p plus 1 square is greater than the fifth root of 2 divided by p square. Then if we add 1, we are sure that this is strictly greater than this one. So we have no solution for this equation. This is a real number. This is a real number. Real number plus 1 square, the fifth root, is strictly greater than the fifth root of this real number square. If we add 1 here, it will be clearly and obvious that this is greater than this one. We can study it as a function if we want, but this is sufficient as a remark. We have no solution. This means that this equation, it is not verified. This means that there is no p such that this is true. Since there exists an element x such that this is not true, this means that this is true and it is not periodic. How about f3? f3, it is periodic, since all constant functions are periodic. f3 of x, which is equal to 3, is periodic. All real numbers are period, but the smallest one doesn't exist. The smallest one doesn't exist, since we cannot find a real number which is just greater than 0. The smallest one, does not exist. So we have not the primitive in this case. How about f4 of x, which is equal to the square root of x? f4 of x, which is equal to the square root of x. The domain of definition is equal to 0 plus infinity. It cannot be a period. It cannot be periodic, since we have here a problem with the negative real numbers. If we take a period here, if we take 0 minus the period, it cannot be true, this one. And the second, we suppose that we have a period such that the square root of x plus p equal the square root of x. We take power 2, we get x plus p equal to x. We cancel x with x and we get p equal to 0. P equal to 0 isn't allowed. What we can say for f5 of x, f5 of x isn't periodic. f5 of x, which is equal to x over absolute value of x, isn't periodic. Why? We suppose that it is periodic. This means that for all x in R star, and for all there exists p greater than 0, such that what? Such that f5 of x plus p is equal to f5 of x. And here we have to discuss cases if we are close to 0, from a side we have -1 and from a side we have 1. This will be false, so it is not periodic. I can detail this as follow. We suppose that this is true. This means that what we have, this means that we have from side x plus p absolute value equal to x divided by x. And here this is 0, which is a forbidden value, and we have p is positive, so we take here minus p, which is also a forbidden value, and here we have x minus infinity plus infinity. X, it is here negative and positive, and x plus p here is negative and here is positive. In this case we have negative equal to negative. It is okay. In this place we have positive equal to positive. We have 1 equal to 1. It is okay. Here we have -1 equal to -1. It is okay. But in this interval we have here we have -1, and this we have +1. So this is not true. It cannot be true. This one we can take x equal, for example, to 1, and then we will, this in general case. But if we take x equal to 1, in this case we will get here 1,